Welcome, dear participants, to our online series Medium Voltage Technology Essentials. My name is Pedro Gomez. I work as a Product Lifecycle Manager for air-insulated medium voltage switchgears, and today I am here with my colleague Miriam Johansson, who works as a Product Lifecycle Manager for gas-insulated switchgears.
I would like to share my personal motivation for creating this training with you. I've been working for Siemens AG since 2017. As a mechanical engineer, I switched from the agricultural and construction equipment industry to medium voltage technology, with which I had hardly any contact at that time. I would have appreciated a compressed basic training when I started. So, I'm more than happy to welcome you to this series.
The Medium Voltage Technology Essentials series comprises 7 informative videos organized into 3 comprehensive blocks. My colleagues and I will guide you through the topics of power supply, components of a medium voltage switchgear, design criteria, construction of a switchgear, our medium voltage portfolio, as well as the current topics of digitalization and sustainability.
Should you have any questions during our series, please do not hesitate to use the Q&A feature located in the upper right corner of this platform. We will ensure that each question receives a detailed response via mail after the event. If you are in full screen mode and cannot see the Q&A field for questions or the chat box, simply press the escape key to exit full screen mode. Now, enjoy your journey on improving your knowledge of medium voltage technology.
And to conclude with the words of the Chinese philosopher Laozi, learning is like rowing against the current. If you stop, you drift back.
Welcome to our Medium Voltage Technology Essential series. My name is Samuel Santana and I am Product Lifecycle Manager at Siemens. And I am happy to present today's session on electrical power supply, switchgear and switches. Before we start, here is a brief outline of today's agenda. In this session, we will cover 5 key topics related to energy. Understanding the basics of energy and its daily impacts is important, as it is a crucial topic that is involved in every aspect of our lives. To wrap up, we will explore some cutting-edge applications that are transforming the industry. Our agenda includes energy transformation, voltage levels, network structure, network restructuring through renewable energies, and applications. Let's begin with the first chapter, energy transformation. Energy is an exciting topic. We all enjoy the benefits of energy every day. But let's define first, what does energy mean? Energy, by definition, is the capacity to perform a job or produce a change. It exists in many forms, such as mechanical energy, electrical energy, thermal energy, and many others. Essentially, energy is what allows objects and systems to perform actions and undergo transformations. On one hand, mechanical energy, for example, can be transformed by means of 2 interlocked gears. When the first gear rotates, it produces a rotation on the second gear. The radio of the gears determines speed and torque. They are used in various applications to increase speed, increase force, or change motion's direction. Gears can be also used to provide mechanical control, for example, in medium voltage switchgears. On the other hand, electrical energy can be transformed by means of transformers. The alternative current flows through the primary coil. It increases the magnetic field around it. As the core of the transformer is typically made of iron, the magnetic field is then concentrated in this core, and it induces a voltage in the secondary coil. And important here is that depending on the type of transformer, this voltage can be either increased or reduced. Electrical energy not only can be transformed, in fact, electrical energy needs to be generated first. The simplest method for electrical energy generation is a 3-phase generator. A 3-phase generator produces electricity by converting mechanical energy into electrical energy using 3 separate coils placed 120 degrees each other. The moving part of the generator, better known as rotor, creates a rotating magnetic field as it spins. This field is typically generated by permanent magnets or electromagnets. As the magnetic field rotates, it induces an alternating current in each of these coils. These setups produce three separate alternating current waveforms, which are also 120 degrees out of phase each other. These waveforms are combined to provide a continuous and balanced power supply, which is more efficient and stable than single-phase power. The power then is distributed through three active wires and one neutral wire, ensuring a steady and reliable flow of electricity. This type of electricity is known as three-phase alternating current and is widely used because it reduces the risk of power surges and improves the performance on electrical equipment. The main characteristics of the alternating current is that the flow of the electrical wave reverses periodically in direction and amplitude. The amplitude is the maximum value of the wave, measured from the zero line to the peak, either positive or negative. The amplitude then represents the power of the wave. It's measured in volts and is directly related to the energy carried by the wave. Please keep in mind that higher amplitude means higher voltage. With this knowledge, we are now ready to get down to business. Different voltage levels are needed to transmit and distribute electricity effectively. But why does the voltage have to change so much? Let's have a look. This is a common architecture of a power grid. Power grid is the network that includes all the infrastructure needed to generate, transmit, and distribute electricity. It ensures that electricity reaches consumers efficiently and reliably. The infrastructure of the power grid involves essential components like power generation plants, transmission lines, substations, distribution substations, and cable infrastructure. In the last chapter, we learned about energy generation, energy transformation, and voltage amplitude. Please observe that all these concepts are in this power grid. And I ask you once again, why does the voltage need to change so much? What's the reason behind that? Large power generators are typically located depending on the presence of primary energy resources, on the availability of cooling systems, and on other ambient conditions. Therefore, they are usually located at some considerable distances from the consumption centers. The transmission and distribution network does not just link substations over long distances. They also form a supra-regional backbone which reserves capacity to ensure a reliable supply and for balancing outload fluctuations. Most of the electrical devices in the household operate in low voltage. A lot of industries use machines which operate in medium voltage. However, representative energy losses can occur over the very long distances that the energy needs to travel from power generation to final consumption using these voltage levels. To minimize these transmission losses, it's preferred to use high operating voltages. High operating voltages means current reduction and means less energy losses over very long distances. When energy reaches urban areas, then the high voltage steps down to medium voltage to be distributed inside the urban areas and to be consumed by industries. When energy reaches final consumers, like residential buildings, then the medium voltage is stepped down to low voltage to be customized and used by final consumers. In all this process, there are two parts which are very important: transmission and distribution. On one hand, transmission is the stage where electricity is transported over long distances from power generation to power consumption, usually above hundreds of kilometers. Transmission is widely known for using high voltage levels, typically above 100 of kilovolts. However, in some countries, transmission can also use medium voltage to carry electricity between urban areas over shorter distances. On the other hand, distribution is usually the stage before and after transmission. It means the stage where electricity coming from power generation is injected into the power grid, and the stage after, where electricity is taken from the grid to be distributed to the consumers. Generally, the voltage level classifications are low voltage, using voltages from 120 volts up to 690 volts, medium voltage, using voltages from 1 kilovolt up to 52 kilovolts, and high voltage, using voltages from 72.5 kilovolts up to more than 1000 kilovolts. The exact ranges depends on the source of information, such as international standards, academic articles, or industrial sector guidelines. Nevertheless, this classification is widely accepted and accurate. Here we have some of the main components used in each voltage level as examples. Please have a look at them with special attention to the size. The size of electrical components increase at higher voltage levels. This increase is due to several factors like insulation, because higher voltages require more insulation to prevent electrical breakdown and ensure safety. This additional insulation increases the overall size of the equipment. A second factor is clearance and creepage distances. To prevent arcing and ensure safe operation, higher voltages equipment needs greater distances between conductive and grounded parts, leading into a large physical dimensions. A third factor is heat dissipation. Higher voltages equipment often generates more heat, which requires larger components and cooling mechanism to dissipate this heat effectively. And the last factor is mechanical strength. Equipment operating at higher voltages needs to withstand higher mechanical stress, which can result in larger and more robust designs. As a result of this, and to ensure reliable and safe operation, the size of components are inherently larger at higher voltages. Now, according to international rules, there are in principle only two voltage groups. The first group is low voltage, which are voltages up to and including 1 kilovolt. And the second group is high voltage, which are voltages above 1 kilovolt and can reach levels up to more than 1000 kilovolts in some countries. Medium voltage is defined as the range above 1 kilovolt up to and including 52 kilovolts. It is really a sub-range of high voltage that serves as a bridge between low and high voltage systems. It's very relevant to distinguish between different voltage ratings in medium voltage. There are several reasons of using different voltage ratings. Some reasons are efficiency in power distribution. Higher voltage reduces the current. Lower current means a reduction on the cable cross-section, which has a direct impact on the cable cost. Low current also reduces the losses due to cable resistance. This makes the power transmission more efficient over distances. Another reason is optimizing equipment size and cost. Different applications require different voltage ratings. By using the appropriate voltage rating, we can optimize the size and cost of the equipment. Another reason is safety and reliability. Using different voltage ratings allows a better control over safety and reliability. Lower voltages, for example, are safer for residential and commercial uses, while higher voltage are used in the industrial sector where equipment are robust, designed to handle its safety. And finally, another reason is load management. Different voltage ratings allow effective load management. Let's imagine we have a cable distance of 20 kilometers and we need to carry on 25 megawatts over there. In principle, we can use whatever voltage rating we want. Nevertheless, please observe that the lower voltage, the more losses we have. For example, in 6 kilovolts, we have more than 40% of losses, while in 30 kilovolts, we reduce these losses to nearly 2%. This is efficiency. As a rule, we can say that we need to increase 1 kilovolt per kilometer. In this way, and by using different voltage ratings, we can ensure that power distribution is efficient, cost-effective, safe, and reliable. With a clear understanding of voltage ratings, Let's now explore how network structures are shaping medium voltage systems. Network is a system designed to generate, transmit, and distribute electricity to various consumers. It consists of several key components like power generation, transmission, distribution, and consumption. We will focus on distribution. Distribution is located in medium voltage level, and it is the process of delivering electricity from local substation to homes, industrial sector, and other end consumers. To manage and deliver this electricity in the most efficient way, two types of distribution are mainly used: primary distribution and secondary distribution. Let's explain both. Primary distribution is typically known for carrying on higher current and withstanding higher short-circuit values. It is also used to deliver power from main substations to several distribution substations closer to the consumers. It is also suitable for delivering a large amount of energy for industrial consumption. And secondary distribution is better known for carrying on lower currents and withstanding lower short-circuit values. It is used to deliver power from the distribution substations to the final consumption, making it suitable for end consumers and applications. Primary and secondary distribution work together to ensure that electrical power is delivered efficiently, safe, and reliable. The quantity of the components needed in the distribution network can be associated to a pyramid for an easier understanding. This is very simple. The higher voltage level, the less quantity of components, and vice versa. The lowest voltage level, the more quantity of components. The logic behind this is very simple. We reduce the voltage level to distribute and deliver power to the consumers. The more power demand and the more consumers, the more components we need to distribute this power, right? Let's imagine this example. Let's say we have a city with roughly 2.5 million inhabitants, with a power demand of more than 1,700 megawatts. The design of the network involves several components. There is no rule regarding how many components are needed. However, as a general overview, we could say it from the top to the bottom that on the top of the pyramid, we need to start with high voltage. For that, we will need 22 substations, each one of them with a capacity of 80 MVA to reach the total power demand. 44 transformers. Here, we can consider 2 transformers per substations. Each one of these transformers with a capacity of 80 MVA, but with a performance of only 50% for security and reliability. The purpose of these transformers is to step down the voltage from high voltage, transmission, to medium voltage, distribution, and starts the power distribution. For medium voltage, we will have, in primary distribution, 770 medium voltage circuit breakers. Just a small quantity of these circuit breakers will be used as main feeders to protect the transformer located upwards. The rest of the circuit breakers will be used as feeders to distribute the electricity downwards. In secondary distribution, we will have a total of 3,520 ring main units to distribute the power in smaller groups. Downwards, below each ring main unit, we will need one transformer with a capacity of 1 MVA. It means we will have the same number of transformers as per ring main units. The purpose of these transformers is to step down the voltage once again, but now from medium voltage to low voltage and reach the final consumers. Then it comes the final stage on the bottom of the pyramid, meaning low voltage. And here is where the quantity of components really starts to increase. It basically depends on the number of consumers. I will not go into more details, just observe please that the quantities are enormous compared with the first 44 transformers, for example. But important here is to ask you, did you notice the rule? The higher voltage level, the less quantity of components, and vice versa. The lowest voltage level, the more quantity of components. This is a simple example to give you an idea about how many components are required depending on the voltage level. A substation is an important part of the power grid. It's part of the infrastructure to deliver electricity to the consumers. A substation steps down high voltage coming from transmission to medium voltage, which is essential for an efficient and safe power distribution to the end users. Commonly, high voltage comes to the substations via overhead lines, while medium voltage is handled inside the substation via medium voltage switchgears and medium voltage circuit breakers. Therefore, substations consist of power transformers and switchgears, which can also be indoor or outdoor. There are some other components related to other critical functionalities like measure, control, automation, communication, or monitoring. These other components enhance the operation as they can provide a high degree of digitalization, automation, and remote control, which means site operation without personnel. Now let's go closer to the end consumers. This is a secondary distribution substation, which is a facility that steps down the medium voltage coming from the main substation to low voltage for final consumption. These types of substations are typically located close to the end consumers. Some of the main components of the secondary distribution substations are medium voltage cable entry for the energy coming from the power grid, one medium voltage switchgear to receive this power, one transformer to step down this medium voltage to low voltage, and one low voltage switchboard to deliver this low voltage to final residential consumption. Typically, at this point, the cable infrastructure flows underground. However, depending on the design and existing infrastructure, sometimes it can also be via overhead lines. Now let's focus on some of the main functions of secondary distribution substations. One very common function is protection and control, as they include circuit breakers and/or fuses to safeguard the distribution network from faults and overloads. Another function is voltage regulation, as they keep the voltage levels within specified limits to ensure a stable and safe power supply. And last function is monitoring and communication, as they have systems to monitor the performance and to communicate with the central control systems for efficient management. These tasks ensure that electricity is delivered to the end user safe, reliable, and efficient. There are basically two types of cable infrastructure: overhead lines and underground cables. Choosing between both depends on various factors such as cost, maintenance, environmental impact, and reliability. Let's do a breakdown for a comparison. Overhead lines are generally cheaper to install due to the less expensive materials and simpler installation process, while underground cables are quite more expensive to install at the beginning due to the complexity of the civil work. Overhead lines have a comparable operational cost for maintenance during their lifetime as they are exposed to open air. However, they have the advantage that when a fault occurs, it is relatively easy to localize and repair. In comparison with this, the operational cost for underground cables is lower as it is protected by the self-infrastructure underground. However, reparations due to faults can result in very expensive costs due to the materials, machinery, and challenging civil works. The visual impact of overhead lines may face opposition in scenic or urban areas. Therefore, they are highly used for long distances in rural areas or in areas with less density population. Underground cables have, in comparison, a minor visual impact, which makes them suitable for urban or densely populated areas. As the faults in overhead lines are easier to localize, it reduces the downtimes. However, since they are in open-air conditions, it makes them more susceptible to being damaged from storms, lightning, and other weather conditions. In the other side, faults in underground cables can be harder to localize and repair, leading to longer downtimes. However, they are less affected by weather conditions, reducing also the risk of outages. Finally, the lifespan in overhead lines and in underground cables can vary significantly due to their different environments and maintenance needs. While overhead lines generally have a bigger lifespan because of the maintenance, underground cables have a lower lifespan because even if they are protected by weather and physical damage, again, it is more challenging and costly to repair and replace. As you can see, both have advantages and disadvantages, but when to use each of them? It really depends on many factors like local requirements, urbanization plans, existing infrastructure, weather conditions, budget, among many others. The use of specific medium voltage ratings can vary significantly by region and country due to several factors. For instance, due to historical development, due to standards, due to safety and compliance, due to climate and geography, due to infrastructure cost, or due to energy efficiency. But no matter the reason for using a determinate rating voltage, they often persist over the years due to the high cost of changing the existing infrastructure. Here is a general overview of the voltage ratings prevalences, taking Germany as an example. 12 kV is the most common voltage level, commonly used in urban areas for distributing electricity to residential and commercial buildings. 24 kV is used in suburban and semi-suburban areas. It can handle higher power demands and longer distances. It is also used for integrating renewable energy sources like wind and solar farms into the grid. Finally, 36 kV is less common but still used in rural areas and longer distances from power transmission, making them cost-effective for sparsely populated regions and for heavy industrial applications where power demand is critical. It's now time to talk about another important and relevant topic, which is the energy source and how this is restructuring the network. Here we can observe the energy consumption, taking Germany as an example. Energy consumption has barely fallen in the last decades. In the long term, heat consumption has decreased, while fuel and electricity consumption has remained almost constant. However, electricity generation is currently mainly based on renewable energy resources, which are gradually becoming more important. Wind and solar generation are good examples of these renewable energy sources. Did you know that the total energy consumption in Germany in 2022 was 2,368 terawatts hour? Well, now you know it. And please keep this number in mind. Now let's break down these 2,368 terawatts hour per sector. To give you an overview about how renewable energy resources are gradually becoming relevant in all sectors, let's review this graphic, which shows the energy consumption in the main four sectors, like industry, household, trade, commerce and services, and transport. The final energy consumption in the industrial sector has remained almost constant over the last 3 decades, but as mentioned, the energy sources have slightly been changing over the years. Please pay attention that an important part of the energy consumption is the electricity coming from renewable resources. As we can see, electricity plays an important and relevant role in terms of energy consumption. And the good part of this is that every day the electricity comes more and more from renewable sources. The energy supply transition has considerably grown during the last decades, from 26.2% in 2014 to 52% in 2023. In 2023, a total of around 515 million kilowatts hour of electricity were generated in Germany. More than half of them come from renewable sources. Compared to the previous years, onshore wind energy was able to increase its generation. The last 3 nuclear power plants in Germany were shut down in April 2023. Electricity generation coming from lignin and hard coal fell sharply compared to the previous year. With the shutdown of the last nuclear power plants, this amount of electricity has been replaced by imports, mainly coming from Denmark, Norway, Sweden, and the Netherlands. This transition is in line with the commitment to the environment. The energy supply transition has then at least three relevant implications for the power grid. The first one is grid modernization and expansion. A second one is grid stability and flexibility. And the third one is decentralization. These changes in the power grid are essential to support the goals of reducing greenhouse gas emissions and increasing the share of renewables. Energy supply transition brings many changes in the power grid and in medium voltage switchgear. For example, more voltage switchgear will be needed to support the modernization and expansion of the grid. Digitalization is now integrated in medium voltage switchgear to combine and create advanced technology for the grid to become a smart grid. As a result of this decentralization, now we have more small-scale renewable power generation installation coexisting together. New applications are now connected to the smart grid. Applications like electromobility, data center, and power storage, just to give you some examples. Today, more than ever, medium voltage switchgear are in demand worldwide. Urbanization, electromobility, climate change, demographic change, flexible working are some of the global trends which are making big changes in the world. For that, the network infrastructure needs to be modernized and expand, and this change needs to be intelligent and fast. Let's have a look at some applications where medium voltage switchgear are used. Medium voltage switchgear are widely used in various applications due to their crucial role in ensuring the safe and efficient distribution of electrical energy. Nevertheless, associated with the activity and sector, electrical applications may have different electrical needs and characteristics which deal with specific technical requirements for medium voltage switchgear. To wrap up this session, let's have a closer look at some of these interesting applications. Data centers, for example, is an application which manages big data as well as uncountable online processes. For that, the medium voltage switchgear in data centers needs to be reliable and provide a redundant power distribution in order to ensure continuous power supply and minimize downtimes, which is very critical for data integrity. Switchgears needs to be also expandable to support scalability as power demand increases. Semiconductors manufacturing is an application with very demanding manufacturing processes. It needs a clean environment, stability, and precision. In this application, medium voltage switchgear needs to ensure a stable and precise power distribution to sensitive manufacturing equipment, reducing the risk of defects. Even more, medium voltage switchgear needs to be compact and seal-designed to minimize contamination. As the manufacturing process starts to demand higher power, an increase in the current capacity of the switchgear is also required. Fast charging stations are a critical part of electromobility. For that, medium voltage switchgear needs to support them with the required power demand, ensuring a safe operation in public as well as in private charging infrastructure. Switchgears also need to be as compact as possible and suitable to operate in open-air installations when required. Wind onshoring power generation is another very interesting application. For that, the switchgear needs very special features. For example, they need to withstand vibration stress and harsh environmental conditions. Due to the fact that the switchgear is installed inside the wind turbine, and due to the height of the wind turbine and the strong wind, they tend to swing around 1 meter on the top. This causes some vibration at the bottom of the tower, where many times the medium voltage switchgear are installed. Switchgear also needs to have a compact design which makes them ideal for being introduced through the narrow door of the tower. In transportation, medium voltage switchgear needs to ensure high reliability and safety. They need to ensure uninterrupted power supply for critical transportation infrastructure, providing protection against electrical faults, ensuring passengers and operational safety. For rail power supply, for example, depending on the country and infrastructure, switchgear may have 1, 2, or 3 phases. They sometimes also need to be provided with high switching cycles due to the high performance of the application. Shipbuilding is an application characterized by very hard conditions. For this, switchgear needs to be robust and withstand the vibrations, shocks, and harsh conditions of the marine environments. And at the same time, they need to be encapsulated to operate in a salty and high humidity atmosphere, and compact to fit well in the limited space available on ships. There are some other applications with high demanding requirements, like the steel industry. Due to the high power demand and heavy machinery, in this application, medium voltage switchgear needs to have a high voltage and current capacities and extremely high operating cycles. They also need to have a high durability design to operate in the harsh conditions of steel plants. Just to give you an idea, a switchgear in many common applications may switch around 1 time per year, maximum 2, and only for inspection purposes, while a switchgear in the steel industry can switch over 100 times per day. This is an incredible performance requirement. Finally, another very interesting application is brown coal mining. For this application, the medium voltage switchgear needs to be installed in the large-scale excavator, and due to the strong and continuous vibration, the switchgear needs to have an additional qualification test for vibration and shock stress resistant. They also need to have a robust design to withstand the dusty and harsh mining environment, as well as a high power handling to support the heavy machinery using in mining operations. I hope this session has been both interesting and highly beneficial to you. Do you want further information, or do you want to participate in an on-site training? Please do not hesitate to contact us. Thank you for participating in this session.